we were talking about the amazing links between cosets and equivalence classes in the special case when your equivalence relation is of this form. And why this amazing connections between equivalence classes and cosets? Well, here's a clue. So when your equivalence relation is defined this way, look at this. This is from theorem 46, and that was a theorem about cosets. And look at that. See, here and here they're the same. So that may make you suspicious that you can link in close ways, intimate ways, a coset and an equivalence class. So what we're going to try and do now is to actually prove. There's quite a bit of proofs, and I've written up some of the prerequisites. We're going to combine elements of two proofs. So a two-part proof, theorem 46 from the chapter on cosets, okay, and a recent proof on from theorem 55, which is on equivalence classes. And this third part, I just call it C because from the previous session, which defines the equivalent relation in these terms. So combining these three, we can prove two interesting theorems. Well, they're not labeled theorems, but results. Okay, so one of them is, given all this, if two elements A and B are in the same coset, then, well, if and only if, then the two equivalent classes of A and B are in fact the same. Okay, so that's one result we'll prove. So, and the second one is that given this, if this is your definition of equivalence relation here, then your A bar, in other words, the equivalence class of element A, and the coset of element A, in fact, the same. They're the same subset. Right? So we'll prove that as well. So again, pretty dense reasoning. It seems to be the pattern increasingly. We're getting towards the end of this course. So lecture 16. There are 19 lectures in the whole course, and definitely higher level senior, verging on M1 first year master's level. So expect the reasoning to become tighter and less obvious, I guess. So non-trivial. All right. Okay, so let's try to prove that if A and B are in the same coset, then the equivalent class of A is equal to the equivalent class of B, and the other way, because it's an if and only if. Right? As usual, let's do the if case first. So that's from the right-hand side to the left-hand side. Okay. All right. So we start with this. A inverse B belongs to H. Now I've written these out because I'll be referring to them a lot. So I just these are sort of comments that help the reasoning. Okay, we're starting with this. Starting with this here. So equivalence classes are the same. A bar equals B bar, and we have to prove it from right hand side to left hand side. So we have to prove that A, B are in the same coset, given this. All right. So we start with this. Here it is here, and from this we deduce that A and B are A is equivalent to B. Where does that come from? Well, using 55.2. Here's 55.2. So if A bar equals B bar, now this is an if and only if, goes both ways, right? So if that's true, then this is true, right? Now we started with that here, so we can deduce that from 55 part 2. So we can deduce this, and there it is, right? Okay, so now we have this. Now using C, if we have this, we can go from left to right and prove that A inverse B belongs to H, right? So we prove that. Okay. Now using 46.2, this result, now this goes both ways, right? So we can go from the right hand side to the left hand side. So if we have this, we know that, right? So A inverse B belongs to H, so we can deduce AH as BH. So we now have this, right? And now using 46 part 1, so that's this part. If we have AH equals BH, we can go from right to left and deduce A and B are in the same coset. A and B in the same coset. Now, if that's true, then that. And 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 if that's true, then this. Okay, so through that chain of logic, if A is B and B is C and C is D and D is E, therefore if A then E. Right? So if this, then through this chain of logic you end up showing that AB is in the same coset. Right? So quite a lot of deduction there. Now let me make a general comment. If you're studying the textbooks for this kind of stuff, you'll find it hugely more compact than what I've given you here. I've spelt it out, I think, a lot more clearly than the text. So this took me some scratching, but I think this way it should be clearer. Right? Now the only if direction. So we are only if, that means from left to right. So we start with this, and we have to prove that. Right? So we start with A and B are in the same coset. All right. So we start with this. Now if we use 46 first part, that's this. So if these, now it's an if and only if, so it goes both ways. So if that's true, this will be true. Okay. So so we get AH equals BH. If that's true, we get this. So we have AH is BH. Now using 46 the second part, so we use this. Now again, if and only if goes both ways. So if AH is BH, we know that A inverse B belongs to H. We know that, right? So from this we can deduce that, right? Now using C, this result, if we know A inverse B belongs to H, we can deduce A is equivalent to B, right? So we get that. So now we've got A is equivalent to B. And now using 55 part 2 here, that goes both ways, right? So if A is equivalent to B, then these two equivalence classes are the same. So we deduce that. So if we start with this, we get that, and hence we can deduce that, hence we can deduce that, hence we can deduce that. Right? So in short, with that chain of logic, so if A and B are in the same coset, then this. In other words, the two equivalence classes are the same. Right? So we've done it both ways. We've done it if and only if, and therefore A and B are in the same coset if and only if the two equivalence classes are the same. So on the left-hand side, we're talking about cosets, and the right-hand side, we're talking about equivalence classes. So obviously they're intimately linked in the special case when your equivalence class here is defined in this way. And the reason for the links is because of this and this. Right? So we have similar relationship here in the context of cosets, and here in the context of equivalence classes. But it's the same terms here, these terms. Alright. Okay. Now, doesn't that make you suspicious that in fact once you deduce that, doesn't that make you suspicious that the equivalence class and the coset are actually the same thing? They're the same set. They have the same members. So that could become like a hypothesis, a theorem statement. Let's try to prove it. So imagine you're a research mathematician and you discover all this, and then you start wondering, well, is it possible that this actually equals that? So I've got a question mark here. So your equivalence class for member little a, is that the same thing as the coset for member little a? So are these two the same? Well, let's try to prove that. Now, what are these two things? Well, they're both subsets of big A. They're both subsets, so sets. Okay? Now, how do you prove that two sets are equal? I've done this many times now. Well, you prove that one's a subset of the other, and the other is a subset of the one. So to prove that these two are equal, we have to do two proofs, two subset type proofs.